Hey everyone. Got a minute or so before class starts, but y'all are welcome to ask me questions if you have any right now. I do have a practice test coming. I'm thinking I'll probably put it up while y'all are doing your lab. I'm probably gonna have two of them. One so you can use to test your Respondus lockdown browser, make sure that your computer has the capability of doing that. And then the other one's just a practice test. I might just make one of them and have it all be the lockdown, but I kind of like the freedom of you guys just taking a practice test without having it locked down. So I might just have a test one and then the other one, but you'll see when it comes up, it'll be one or two of them. Up to 17 participants.
So if we do have an issue using the Respondus lockdown, would we just let you know that we couldn't take the practice test?
Yeah, just let me know soon because the test isn't until Friday, and we can make some arrangements if that's the case. But if it's not, then we'll do that. I might even be able to figure out some way to. I was just looking at this computer screen. You probably see that I've got all the blocks up of all the students. I might consider doing that. As opposed to the Respondus lockdown, as long as everybody's got cameras. You got to have a camera anyways for the lockdown and the other process that Respondus offers. So I might just do it all through Zoom. Only problem is that's such a bandwidth issue, but that would be enough for me to feel justified in that y'all are not cheating.
Gotcha.
So I might do that, but like I said, I want to see how it works out. I think we'll have a pretty good issue with the Respondus. It so far hasn't had any problems with any of the other classes.
Okay, is it like a browser that we have to download, or is it something that's just going to work when we click on the test?
Yeah, that's why you got the practice test. When you put on the practice test with the Respondus one, it'll tell you download something, and like it'll download it for you almost instantly. And it's sort of like Internet Explorer or like Safari if you're an Apple user.
Okay,
so it's a really
thank you.
Trimmed down one. You're welcome. Anybody else have any questions? Ooh, we're up to 19. Shrudi's here, party. All right, well, we should go ahead and get started, even though everybody's not here yet. I'll do the roll a little bit later. I'll give more people more time to get in. It looks like no one has any questions about any particular topics from last time or earlier in the semester. I want to reiterate, some people asked me about this last night, even though I said it last night, even though I told everybody in the meeting last time. This midterm is a midterm, so it will be somewhat comprehensive. And what I advise everyone is that it would surprise me if you didn't get at least one question regarding vectors, meaning like calculate the vector force due to a Coulomb force, or calculate the electric field in vector format for a charge distribution or something like that. I just one of the things we got to make sure students can do every semester is that they can add, subtract vectors. So, being able to break a vector down into its components, add the like components, and then rebuild it up into a new vector is a skill that you're not allowed to leave 202 without. You're not allowed to leave 201 without either. So I'll probably have something like that on the actual midterm. Other than that, it probably won't be that comprehensive, except for the fact that all the principles you've learned in the past are always fair game. So hopefully that clears that up. I guess we can go ahead and get started then. One more chance. Anybody have any questions? The 20 participants now. Any questions on anything? I'm looking at my chat as well. All right. So what we're going to do here is we're going to, I don't know what just happened. Yeah, just hit one button. Why did it do that? Oh, exit full screen. Let's do speaker view. Okay, that's what was going on. So last time we sort of finished up our understanding of the early quantum mechanics, the Bohr model, the atoms, stuff like that. Now we're going into today, and we're going to actually skip chapter 29, which is kind of a bummer. I really like to cover 29. It helps you more when you get to your chemistry class, or if you've already had chemistry, it'll make your chemistry make a little more sense. So whoever gets to teach it second, whether it be the chemistry instructor or the physics instructor, gets the credit of like, oh man, that person made it so much more understandable. So anyways, I do like teaching that. If you're having any difficulties understanding what you got out of chemistry and your major actually depends on chemistry, I would highly recommend you read chapter 29. But anyways, let's go ahead and talk about what we're talking about in the quantum mechanics of atoms. So when Bohr came up with his quantum model, he basically had one quantum number. That quantum number was n, and it turns out to be the same quantum number that we use now as n, and we call that the principal quantum number. But future experiments after that showed us some weird things were going on, so we ended up having to come up with a bunch more quantum numbers, and that was kind of nice because it ultimately helped us understand the way atoms interacted with one another to make compounds and stuff of that sort. So it was all in the end just something that made us deeper, give us a deeper understanding of nature and how it works. So we're going to go over that kind of stuff today. You'll learn how to fill in the orbitals for electrons for a given element, so on and so forth. And talk about the Pauli exclusion principle, things like the Zeeman effect and space quantization, and stuff that sounds a lot cooler than it really is. But anyways, it is something important. So let me turn your attention to my document cam, where I've written up some stuff just to make sure you guys have a nice clean picture of what we're looking at. So what Bohr found is that the energy really only depends on the principal quantum number n, okay? And that's more or less true. We've found that actually you can you can change the energy slightly by changing other quantum numbers, but it's really just a small effect. So in general, that particular fact that En is equal to some value over n squared is pretty realistic, but the negative 13.6 is only what it is for hydrogen. So we turn out that, yeah, it's going to be some energy like this. It's going to be somewhat inversely related to n squared, but it'll be different. This number will be different for every atom. Not only that, there will be small, what we call perturbations to the energy for other quantum numbers. We're going to basically ignore all those for this discussion, just because it gets way too deep in the weeds for someone who's not going to major in quantum chemistry or physics. So first off, we found the principal quantum number, and now we're actually at a position where we can say what that means. And it seems that the atom has shells, and one shell can contain several subshells. And those shells are what sort of contain the electrons, if you will. So the principal quantum number tells us what shell we're in. And the shells are weird in that most people hadn't heard of them, but they're the K shell with a capital K, the L shell with a capital L, the M shell with a capital M, and K, of course, corresponds to n equal 1, L corresponds to n equal 2, M corresponds to n equal 3, so on and so forth. You'll see where that comes in later. We don't even use those K-shell notations when we talk about the electron configurations of atoms, but it'll come up later when we talk about X-rays and stuff of that sort. So that's the principal quantum number, which we sort of, in the Bohr model of the atom, just took as the one orbit, the number that decided what orbit we're on away from the nucleus. So n equal 1 meant the orbit that was closest to the nucleus. N equal 2 in the Bohr model meant the second closest. N equal 3 meant the third closest, so on and so forth. Now we're going to see it's a little bit more complicated than that, but the fact is n is still 1, 2, 3. It can be up to infinity. So any number, 1, 2, counting number up to infinity, basically, but not 0. Okay. We've also discovered there's another one called the orbital quantum number, L. And the orbital quantum number gives us basically a measure of the orbital electron angular momentum, as does ML for that matter. But that quantum number is lowercase l, and it goes from 0 So 1 to 2 to 3. So it counts as well, but it stops at n-1. So if n equals 1, L can only be 0 because 1 minus 1 is 0, and that's the smallest number it can be. If n equals 2, that means L can be 0 or 1. If n equals 3, that means L can be 0, 1, or 2. Does that make sense? Now, those quantum numbers turn out to be what we call a subshells, and these are the things you probably do remember from high school chemistry. If you remember, there was the spherical one, and then you went to one that looked like two balloons who had their you know, the opening where you tied them up in a knot. They had them turned towards each other, and then there was a little donut around them. That was p orbital, and then you had another type of spherical one and stuff like that. Those are the subshells, and these are really defined by the quantum number lowercase l. Now, when I say it's related to the orbital angular momentum, remember orbital angular momentum is basically the angular momentum something has for being in an orbit. So if you imagine the electrons, even if they're a distribution of probability, there is still in some sense an electron orbiting, okay? And that orbital angular momentum in classical physics would have been mass times the radius of the orbit. So the mass of the electron times the radius of the orbit times the velocity. Well, it turns out the magnitude of that quantity is going to be the square root of L times parentheses L plus 1 close parentheses and then 2. So when L equals 0, obviously we're going to get 0 angular momentum. When L equals 1, we're going to get 1 times 1 plus 1, so that'd be square root of 2 h bar. And remember, this is the h bar. This is the h over 2 pi that I talked to you about before. And we don't actually take the time to calculate what h bar is when we're dealing with orbital quantum numbers and orbital angular momentum and stuff like that. We always just leave it in terms of h bar. So that's a little bit of a savior in terms of calculation. If n equals 2, though, it gets a little more complicated. You got 2 times the square root of 2 plus 1, or excuse me, the square root of 2 times parentheses 2 plus 1. Well, 2 plus 1 is 3. 2 times that is 6. So it's the square root of 6 times h bar, and so on and so forth. That's what the orbital quantum number is. Then it was discovered that when you take those spectra, remember the dark fields that had the really bright thin lines on them? It was discovered that when you actually subjected the matter to say in one of those discharge tubes, to a magnetic field, that those very, very crisp lines broke up into 2 or more lines sometimes like 5 and stuff like that. So they discovered that they needed another quantum number to make sense of that, and that quantum number became the magnetic quantum number, m sub l. So far we've got n, the principal quantum number, l, the orbital quantum number, ml, the magnetic quantum number, and again, that's called magnetic because it wasn't discovered until we subjected it to magnetic fields. And it turns out that this ml, if you multiply that by h bar, you get the z component of L. The x and y is more or less indeterminate because of the uncertainty principle, but you can get the z. Now, the deal with the magnetic quantum number, remember n is 1, 2, 3 on up, L is 0 on up to n minus 1. Now, the magnetic quantum number goes from negative L to positive L. So negative L plus 1, negative L plus 2, dot, 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 0, dot, 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 L minus 1, L. So in the case of, let's say, n equals 2, well, in n equals 2, that means L can be 0 or 1. And then that means, of course, that ML can be 0, negative 2, negative 1, 0, 1, and 2. Okay, so that's how that works. And I'll give you some examples in a second, and they'll make a little bit more sense. But this is related to the electron's orbital angular momentum, just like the last one was. But it was, again, found as a discovery under magnetic conditions, and hence we called it it was just called the Zeeman effect. And now whenever we see a splitting of spectral lines, we infer that that is the Zeeman effect, and we automatically start thinking of magnetism. This has happened, for instance, when we looked at the spectrum of the sun. We'll occasionally see that the spectrum of the sun has lines broken up right over top of sunspots. When that happened, we realized, oh, okay, the sunspots in the sun must have something to do with magnetism. So that's a typical discovery that something like knowing the Zeeman effect can help us with. It's also the origin of the terms space quantization. So as I told you, space quantization is not nearly as cool as it sounds, because really what it means is like L, when we were doing the big L up here, that's the total magnitude of the orbital angular momentum. So 0, I think we found the next one was L equal 1 would be 1 times 1 plus 1 would be square root of 2 h bar, square root of 6 h bar, so on and so forth. Well, that's the total angular momentum. So you've got this vector that can point any different way, so you think, but in terms of this quantum number, it's almost as if space is quantized. There's only certain allowed orientations of the angular momentum. So when L is equal to, or M sub L is equal to 0, for instance, it's going to have no z component. So it'll be lying flat in the xy plane. And it's basically just, if we're looking along the z-axis, it's basically any of these positions could be the angular momentum vector. Okay? That's what that, well, I drew an angle at the plane at a slightly different angle than I drew the rest of these, but I still think it makes the point. When you have M sub L being 1 h bar, then you can actually say the z component has 1 h bar z component, so it's really just tilted up a little bit. So if you look at it from the side, it look like that. It's tilted up. But if you look at it from above, it's tilted up that 1 h bar here to here between my two fingers. But it can be any of these positions like this. That's what I'm drawing as a cone there. And when it's 2 h bar, it's obviously going to have a z component of 2 h bar. So it's tilted a little higher, but it still makes a cone, again, just like this. For LZ being negative h bar, it's the inverted cone for LZ equal 1. And similarly, for LZ equals negative 2 h bar, it's again an inverted cone, just like the 2 h bar one. Okay, so that's why I called it space quantization. It looked like there were certain allowed areas of space, and only that. Now, finally, the last one that was discovered, the last quantum number, the principal out of the 4, was called the spin quantum number. Now, this one's kind of neat. This one, there was many ways it could have been found, but it turned out, and I've told you this story before, is Dirac took Schrodinger's equation and realized that it was inconsistent with special relativity. So he just decided to make an equation that was correct with special relativity. And we ultimately called it Dirac's equation. There's some other names for it as well, but we called it Dirac's equation. And lo and behold, that gave us access or predicted another quantum number, and that quantum number became the spin quantum number. The spin quantum number, it's as if the electron is spinning, and because it's a charge, it creates a magnetic moment, if you will, a dipole moment pointing up, or if it spins the other way, it creates a magnetic moment, dipole moment pointing down. Okay. Well, since then, we've discovered there's no way in heck that an electron is actually spinning, because in order for it to have this amount of angular momentum that it ultimately has, it would have to be spinning way faster than the speed of light, because basically the electron size is so small. It's just a weird thing. So all we can tell you is that, hey, this is one of those cases where quantum mechanics something exists that we can't really find that good of an analogy with. We can say it's spin because it says if the electron is spinning, but we know for a fact that's not what's happening. Okay. But the good news is this quantum number is very simple. It's just plus 1/2 or minus 1/2. And that's it in a nutshell. That's the quantum numbers. This actually, these spin quantum numbers actually do affect, just like the other quantum numbers do to a small extent, do actually affect the energy, but the energy change is, again, just what we call a perturbation. It's a very small fraction of the total energy. And it leads to what we call the fine structure of the atom. So what we mean by that is when we start looking at the energies, we see that basically they break up into a little bit more than what Bohr suggested, first by the magnetic quantum number, and then by the spin quantum number. And once we take into account the spin quantum number, that's what we call the fine structure of the atom. There's even hyperfine structures and stuff like that that goes a little deeper. So it turns out this works, and this is actually true for basically all atoms. In fact, we'll even learn when we get to nuclear physics that this sort of rigmarole, these weird quantum numbers, pop up again in the nucleus. So it turns out the nucleus has quantum numbers too, but we're not even going to touch that aspect. We're just going to pretend like the nucleus, since it's so small, it's made up of really small particles, and we're going to ignore the quantumness of it. But it does turn out, just for your ability to succeed on Jeopardy, it does turn out that the nucleus is in fact dictated by quantum numbers as well. So first off, let's give you a little example. When n equals 1, what quantum numbers are possible? Well, first off, we take L. L goes from 0 on up to n minus 1. Well, n minus 1 is already 0, so L has to be, in fact, 0. ML can be negative L on up to positive L, but again, that's just ML is just equal to 0. But then, even in that state, we have the spin quantum numbers equal to plus 1/2, and then and negative 1/2. So what Wolfgang Pauli, first off, his name is Wolfgang. That's pretty bad. He don't look as cool as someone who should have a name like Wolfgang, but he is pretty bad dude. He wrote a textbook on on general relativity at the age of 16, and I actually have a copy of it here, and it's harder to read than all the other textbooks that I used in graduate school. So Pauli's a sort of a brilliant dude. But anyways, Wolfgang Pauli came up with this idea called the Pauli exclusion principle, and the Pauli exclusion principle just tells us basically no two electrons can have the exact same quantum numbers. So what this means is when n equals 1, when you're in the K shell, remember n equals 1 corresponds to capital K, then you only have one subshell, and that subshell is S. Okay, that's L equal 0 is S. And that the M sub L, of course, can only be 0. So that means that basically the angular momentum is 0. But you can still have two electrons, one spinning as if the spin is up and the other spinning as if the spin is down. And again, we're saying the word spin and spinning as if it's doing that, but we know it's not. Okay. Now, if you get a little more complicated and try n equal 2, well, things get a little more dicey. So what we're going to do is write L, M sub L, and M sub S, and just make a sort of table. So n is definitely equal to 2. When n equals 2, then L can be 0 and 1. So first off, if L is 0, we already know what happens. ML has to be 0. And then we know we get two states like that. We get the plus 1/2 and the minus 1/2. I had to write those really small, but I think by knowing that ML is only plus or minus 1/2, you can probably tell what that's going to be, right? So that's just part of it. At n equal 2, remember this is n equal 2 is another shell. In this case, we're talking about the L shell. So for n equal 2, we have L equals 0 or L equals 1. Now we can say, what about when L equals 1? Oh, I wrote L instead of 1. Well, I can write 1 there. And when I write 1 there, then that means M sub L can be negative 1, 0, and 1. So I have 2, 1, negative 1 with a plus 1/2. And then I have 2, 1, negative 1 with a minus 1/2. Then I have 2, 1 with a 0 with a plus 1/2. 2, 1, 0 with a minus 1/2. And 2, 1, positive 1 with a plus 1/2. And 2, 1, positive 1 with a minus 1/2. Okay. So that tells you when we deal with n equal 1, in other words, only one shell, the K shell, we got 2 slots for electrons, period. And that's actually what hydrogen and helium have. If we do n equals 2, then we're up to the L shell. And the L shell actually allows us 1, 2, 3, 4, 5, 6, 7, 8 electrons. Okay, now it's broken up kind of weirdly in that it's got the S subshell, which is the L equals 0, and then it's got the P subshell, that has 6, and that's more like what you remember from from chemistry, is the p orbitals allowed 6 electrons, and the s orbital was just another one just like this guy up here and only allowed 2 electrons. So that's typical examples of what you need to be able to do with this information regarding quantum numbers. Anybody have any questions on that? Okay, so let's remember our quantum numbers are in the principal quantum numbers, and that's n equals 1, 2, 3, and up to infinity. Turns out that that's the thing that has the most effect on the energy. In fact, you can pretty much get a really good estimate of the energy of a given electron just by knowing its n number. But if you want to be as precise as possible, you need to also include the L, the m sub L, and even maybe the m sub S. Okay. In fact, as I told you before, there's a 21 centimeter line that we know of from hydrogen. Basically, it's a radiation that is emitted by hydrogen, but it has to be actual hydrogen that has an electron in it, so it can't be so much of a high temperature. If the temperature gets too high, the hydrogen can't hold on to its electrons. But the cool thing is when the electron in a hydrogen atom switches from spin up to spin down, the energy difference between the two is actually just equal to hc over lambda, but in that case, lambda has to be 21 centimeters. So we can, in everyday life, at least with lab equipment, we can actually determine the difference between spin up and spin down. So it does matter energy-wise. It's just really, again, we're getting into the fine structure of the atom at that point. So those are your 4 quantum numbers: N, L, M sub L, and M sub S. Now it turns out with the Pauli exclusion principle, we also learned something else. We learned that there's allowed transitions and forbidden transitions. They're not related to the Pauli exclusion principle, but because the Pauli exclusion principle taught us a little bit more about how we can fill orbitals of atoms with electrons, this is something else, because now it tells us how we can treat electrons when they try to make a transition from one orbital state to another. It turns out that the selection rules are basically delta L equals plus or minus 1. So remember, your quantum numbers are N, L, M sub L, and M sub S, but we're saying transitions only occur such that the change in L is equal to plus 1 or minus 1. So that's now the selection rule. So according to a selection rule, an electron in an L equal 2 state can jump to L equal 1, or it can jump to L equal 3, but it can't jump to L equal 4 or L equal 0. Does that make sense? I mean, it should make sense in the sense that I told it to you, but not in the sense that it's like anything you've ever heard. All the other ones, those, L equal 2 to L equal 4, or L equal 2 to L equal 0, those are what we call forbidden transition. And strictly speaking, they're not really absolutely forbidden. They can occur. It's just they are relatively rare. So things have to be sitting still without being probed very much for a long period of time before that transition will automatically happen. And we actually can detect those changes happening in nature, again, in the astronomy realm. So those are some neat little tidbits. I will remind you again that basically, if we go to say, let's lay out what the quantum numbers are for the hydrogen atom. So let's do the helium atom. So for helium, which is actually a noble gas, it's, if you see it on a periodic table, it's either in the far left-hand column or it's either in the far right-hand column, because it actually has its outer shell, which is its only shell, the K shell. It has it actually full, but it has 2 electrons. So N equals 0 implies L equals 0, which means ML can only be 0, which means we get a plus 1/2 for MS and a minus 1/2 for MS. Okay, so there's only 2 of those states. So in fact, we'd say that the electron configuration is 1s2. That means N equals 1, L equals S the subshell being S corresponds to L equals 0, And it does happen to be a spherical shell, but that's not why it's called S. It's actually called S because it was seemed to be a sharp line. So there's S, P, D, and F, and your book actually tells you that S is sharp, P is principal, D, I can't remember what that one was, but F was, anyways, well, I'll get to that in a second when I get there. I never remember those ones. The only ones I ever remember, oh, sharp, principal, diffuse, and fundamental. So that was the SPDF. After F, they all just go according to the alphabet. So this tells us N is 1, L is 0, and there's 2 electrons in that state, right? Well, it turns out that electron cloud is basically spherical, okay? And I drew a line to show a border, but there is technically no border. I mean, you could sort of estimate a radius at which you have 99.9% of probability of capturing the electron, and then that could sort of define your line, or you could say it's 99.99 and you get a slightly different line, but that's more or less what's going on. The next one you get, of course, is 2s, and then if you're lucky enough, you have enough electrons, you can also do 2p. Well, the p is the weird one. So this is the s orbital. The p one actually looks like this, that you remember from chemistry. But that's n equal 2, L equal 1, and ml equals 0. So n equal 2, L equal 1, and ml equals 0. But it's not the only one. In fact, you can have n equal 2, L equal 1, and then what you get is a torus, or a donut, if you will. Okay. Again, I'm drawing them as if they're well-defined shapes, but really they're probability distributions with no clear lines. But again, if you tried to find the 99.9%, it would make a shape like this, and the 99.9% would make a shape like this. This is again n equal 2, L equal 1, but it's, in this case, the weirdness is m sub L is equal to plus or minus 1. So either of those is going to give you basically that donut shape. And that donut shape, of course, would be right around this guy. Okay. So when you get into these orbitals, you first got an s orbital that's spherical. Then you got a p orbital that for L equal 1 gives you this double balloon shape, and then for L equals 1 with ML equal plus or minus 1, it gives you a donut around the balloon shape. Okay, so that's some of the stuff that you might remember from chemistry. But if you continue this line here, 3s, 4s, 5s, and these are lowercase s's, 6s, 7s, so on and so forth. Then you say 2p, well, n equals 2 only allows L to be 0 or 1, so I can only have S or P. But n equals 3 allows me to have 3p and 3d. Okay? N equals 4 allows me to have 4p, 4d, and then we go up to basically the L equals 4, and in that case, or excuse me, the L equals 3, and in that case, we end up getting the F orbital, or a subshell, I should say. So that's 4F, and so on and so forth. So when you go to fill in the electron orbitals, what you want to do is basically go along here like this. And this will actually give you your energy. So weird things happen, like you can tell, for instance, that sometimes you'll get a 4s before you get a 3d. And that's very normal. The 4s orbital, because you're coming on this diagonal, the 4s orbital is actually lower energy than 3d. So an electron will fill up 3p and then fill up 4s and then come back and do 3d. So that's why I draw this diagram like this. This is 5p. This is 5d, this is 5f, and ultimately that also allows you 5g. not to be confused with internet. Okay, so if you come at a 45-degree angle, you can see that's actually the way the electrons are filled. Okay, I'd have to fill in more of this to do this one, but I think you can see. So first I fill up the 1s, then I fill up the 2s, then I fill up the 2p, then I fill up the 3s, then I fill up the 3p, then I fill up the 4s, then I fill up the 3d, then the 4d, then the 5s, so on and so forth. Okay, so that is sort of how we map out the Pauli exclusion principle to fill in the electron orbitals such that the energies turn out to be proper. It's not that you can't find an atom that has the 3d orbital filled before the 4s is filled. It's just that atom is in what we call an excited state. So if you come back a little while later, it's going to be back into the 4s instead of to the 3d. Okay. Any questions on that? Hopefully this is stuff you've seen before in chemistry and whatnot. Okay, again, you're not required to have chemistry for this course, but most people have had a little bit of chemistry, even if it was in physical science in high school or actual chemistry course in high school. So the way we look at it is you can say for the hydrogen, it's just going to be 1s1. For helium, it's going to be 1s2. For lithium, that's got 3 electrons, that'll be 1s2, 2s1. For beryllium, it'll be 1s2, 2s, whoa, 2, that's the 4, and so on and so forth. And in fact, if you look at a periodic table like the one in the back of your book, it actually gives you basically the outermost orbital. So if you're looking at, for instance, in helium on your periodic table, it says hydrogen is 1s1, and then it says helium is 1s2. But weirdly enough, it just says lithium is 2s1. But if you look at it, you're like, oh, well, that just means it's helium plus 2s1. So that's the way all of them do. Basically, the last noble gas is where they start at. So the last noble gas was lithium, or excuse me, the last noble gas was helium, and lithium would just be, well, one state beyond that. Again, you could do 2s2 for beryllium. After beryllium comes boron. So with boron, you actually have, in this case, 5 orbitals or 5 electrons. So it's 1s2, 2s2. Now we have to jump up to 2p. Notice the 2p is actually filling before the 3s. So if we look in boron, it is in fact 2p1. If we look at the next element, which is carbon, we get 1s2, 2s2, 2p2. The next element, of course, is nitrogen, which has, in this case, 7. So it'll be 1s2, 2s2, 2p2. But check this out, because it's a p orbital, what do you think is allowed now? Is it just 2 electrons allowed in p orbital, or do we have to jump to the 3s? Anybody know? Y'all can type it in chat if you want. I'm looking at it. So what I want to remind you is 2p means n is equal to 2, but it also means L is equal to, remember, L can be 0, and that's S, or it can be n minus 1, which in this case would be 1, and that's P. So L equals 1 is what's going on there. Well, that means ML can be -1, 0, and 1. And both of those, all 3 of those are each allowed 2 electrons. So 1, 2 for here, 1, 2 for here, and 1, 2 for here. That means it's allowed 6. So I wouldn't have to stop at 2p2. I could use 2p3. So nitrogen actually just ends with a 2p3 instead of 2p and then jump into the S one. After our nitrogen is oxygen, and oxygen, of course, has an atomic number Z equal 7. So 7 means it has 7 electrons. Obviously, we haven't filled up the 2p yet, so we can still say 1s2, 2s2, and 2p4. Fluorine, we can say it's got 9, so it'd be 1s2, 2s2, that's 4. And then plus 5 would be 9, so that's 2p5. And then finally we get to a noble gas, and that's neon. And neon gives us 1s2, 2s2, and 2p6. So not till we get to neon do we jump down to the next order, which is 3s. Okay, so once we're past neon, we start to use the 3s. So you can see, for instance, sodium has 3s1, magnesium has 3s2, aluminum 3p1, weird stuff like that. Remember, s orbitals can only have 2. So that shows you how to use this monstrosity, as well as remembering how the N's, the L's, and the M sub L's, along with the MS's, of course, how those all interact to allow us to figure out all this stuff. So let me ask you a question. Let's see. What if I have 1s2, 2s3, and 2p6? Is that a real electron configuration? Is it possible, I mean? I wrote what I meant to write. I didn't make an error like I often do in class. So 1s2, 2s3, 2p6, is that a possible electron configuration according to the Pauli exclusion principle and our understanding of quantum mechanics? Exactly. This one's impossible. Can anybody articulate why? You can type it if you don't want to speak out. What's wrong with this one? What makes it impossible? Exactly. You can't have 3 in the s orbital. So remember, the s orbital corresponds to L equals 0. And L equals 0 only allows ML equals 0. And then ML equals 0 and only 0 means you can only have 2 electrons there. So yeah, you can't have that. Here's another one. What about is that possible, impossible, or just unlikely in some sense? I gave you the information a second ago to be able to figure this out. See if you can think about something I said recently and see if this one works out. Let's start off with, is it not impossible, but is it, would you be surprised if you found that in the periodic table listed as the actual electron configuration of a particular atom? Anyone? Yes, you would be surprised. The reason you'd be surprised is it skipped the protocol. It skipped the 1s, 2s, 2p, 3s. It basically went from 2s all the way over to 4d. Okay? Now, the deal is it's not impossible though. Okay? So this one is actually what we call an excited state. This is one where the electron, maybe because the, in this case, since it's only 5 electrons, if you assume it's neutral, then it has to be what? Beryllium? No, boron. It has to be boron. In this case, a boron atom might have been at high energy, say in the core of a star, and bumped into something that knocked the electron up from its normal, 3p state, or excuse me, the boron would normally be in the 2p state, excuse me. So it knocked it all the way up from the 2p state, all the way up to the 4d state. So that is allowed, and it is possible. It's just not the ground state of the atom. The ground state of the atom would be just like we see for boron over here, 1s2, 2s2, 2p1. Okay, so those are some of the types of questions you should be expecting. You should be able to, of course, fill out the electron configuration for any atom. And for instance, if we wanted to do, let me show you one more on this, and I'm going to show you a neat notation that's often used, especially in chemistry, and sometimes I use it just to save some time. So we did neon was 10, and we got 2p6. After neon came sodium. Sodium had 11. So obviously it's going to be using that rigmarole up there, that 1s, 2s, 3s. It's going to be 1s2, 2s2, and then after 2s, of course, we got the 2p, and that can only hold 6. But after 2p, we went to 3s. We're now up to 1s2, 2s2, 2p6. So it must be 3s1 because it's just one electron higher than that. So another way we can actually call this is we can say it is neon 3s1, and that's more or less what the periodic table in the back of your book is doing, except it's ignoring writing that because it's really redundant. If you look at sodium, you know the previous element before sodium was neon because it's literally in one row above and immediately the next column over. So that's another way of writing it. You just write that this is the closed orbital and this is 3s. And the reason we do that is the same reason that the noble gases are called noble gases. Basically, whenever you get a filled shell, so in this case we had hydrogen, which allowed one more electron. So hydrogen is very, very, very reactive, okay? And that's basically true about all the alkali metals, all the things in the column 1. And then helium-2 has a filled shell. The shell is n equal 1, and n equal 1 can only have one subshell, that's the s, and the s can only have 2 electrons, so 1s2 is a filled shell. So this is equivalent to just saying helium. So I could replace this right here with that helium symbol and then just put 2SN1 after it. Now, what that means is when you have a shell full, the next jump to the electron orbitals, you can sort of think of it as a big jump. And those ones inside that filled shell are really, really, really reluctant to leave. They've got a lot of forces holding them all into place. A lot of energy is what it takes to actually break those electrons apart whenever the shell is full. And then the outer layer, which is the outermost one, is called the valence shell. And that valence shell, if it's down by 1 or up by 1, it's going to be highly reactive. So that's actually how we can sort of look at the periodic table. In addition to having the periodic table have this wonderful ordering, namely it goes from Z equals 1, which corresponds to 1 proton, and if the atom's neutral, it should be 1 proton, 1 electron, to Z equals 2, which could be in the second column, because all the things in the second column have a full S shell. It's just not necessary that the S shell's the outermost shell, but it could also be, in fact, in the last column because it's a filled shell, and that column is for the noble gases. And then we go to the next one, and so on and so forth. So yes, it goes 1, 2, 3, 4 according to Z, like this. But if you once you line it up like that, what you see is the individual columns in the periodic table give you basically properties. So let me refer you to something real quick. I'm going to share screen. And I think I will share this one. And first off, I'll show you, here's that diagram that I'm drawing, 1s, 2s, 3s, like this. And then you just know that your things fill this way, and then the dotted lines are your missing stuff, and then this way, and so on and so forth. So you can find a ton of those. Now what I want to do is show you a periodic table. hopefully one that they're not trying to sell. Let's just take this guy. Hopefully this will be Wikipedia. Yeah, that would be fine. Okay. Now I want that. I'm going to make this smaller. Make it smaller still. Okay. So what we have here are groups and periods. Okay. So this is the first group. And basically what they all have in common, if you look, for instance, we did hydrogen and lithium. Hydrogen had 1s1. Lithium had 2s1 as its valence. Sodium actually had 3s1 as its valence. So what you can see is each one of these things, even though Mendeleev didn't know it when he put them together, each of these things had very specific properties, and that very specific properties that are common are all in one column. So this whole column, everything acts alike. This whole column, everything acts alike, specifically because its valence shell is an S shell, and it's one shy of being full. This one, on the other hand, this is beryllium and magnesium. We did beryllium, and beryllium has a 1s2, 2s2, because it's 4, and that gives you, of course, a closed outer shell, a closed S shell. Okay. Magnesium, on the other hand, gives you, if you actually looked it up in our periodic table, because this one don't have the orbital configurations, which would have been nice, is a 3s2, and this one's a 4s2, which is calcium, and so on and so forth. So all of these columns all act the same. All of these columns all act the same. Everything in this column acts 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 the same. So on and so forth. And all these things, which you know of as the noble gases, all act the same. They're kind of stingy and don't want to interact with one another. They're uppity. That's why they call them the noble gases. So let me tell you a real life story, and this will hopefully sink it into you what this means. So there's a very important element right here. Anybody know what this element is? I probably need you to speak because I can't read the chat right now. Anyone? Anyone? Ca. What element is Ca?
Calcium.
Yeah, calcium. Why would I say that's important? Anybody know? From biology standpoint.
It's good for your bones.
Exactly. So this is kind of neat. Everything in this column acts like calcium. Okay. And that's neat, and it's horrible. So here comes the horrible part. Madame Curie discovered radium and polonium. Her and her husband both did. When we discovered radium, radium was really interesting in that it glowed. And people were like, wow, this is really cool. So this is around the time of World War I when she discovered it. And this discovery of radium was sort of eye-opening. A lot of people were like, wow, this is really exciting. We can now, use this radium and put it like on the little numbers on our watches. And that actually causes a little glow. So you can actually see the numbers in the night because it'll glow. They didn't know that radium was dangerous. In fact, radium is a radioactive element, and it is horribly radioactive. So it's really, really dangerous. So in the time of World War I and World War II, for that matter, basically most of the men are away. All the work has to be done by the women, and most of them are quite young women because they're the ones whose husband went away. So these women were employed in factories to actually paint on radium on the dials of watches. And what do you do when your brush gets a little fuzzy? You lick it. Well, what was happening is the ladies were licking the tip of their brushes to make them sharp so they could correctly mark the watch, and they were ingesting radium. And they had 22-year-old women come in with broken hips and bones of 90-year-old women. And the reason why was slowly radium had been replacing calcium in their bones, because in the periodic table, radium and calcium are identical. So your body doesn't know the difference. It just starts putting calcium in there. But as you can see, calcium is way, way, way higher up on the periodic table than radium is. So radium don't have the bonding strength that calcium does, even though it looks to the human body like calcium. And that means it can't bond to the other calcium like the other calcium can. So it ended up making the bones very, very brittle. In fact, some of them even glowed in the dark, and they died horrible lives, as did Madame Curie for that matter. We didn't really know, for instance, that radioactivity was dangerous. A guy by the name of Elihu Thompson, who was an engineer, polymath, if you will, else he was a scientist, a mathematician, an engineer, all these different things. He was certain that X-rays and other types of radiation were not dangerous at all because they were so natural. They were naturally occurring. Ergo, they couldn't have been dangerous. So he set about doing an experiment to prove that radioactivity was not dangerous, or specifically in his case, he was doing that X-rays were not dangerous. So he kept a little notebook, as a good experimentalist would do, and he basically would hold an X-ray tube against his hand, against his finger, for on the order of like a minute or two every day. And you read in his journal, and after like 2 weeks, it's like, as I suspected, there's no danger to this. My finger is just fine. But if you skip ahead a little bit, you say, it's been 1.5 years since I stopped the experiment, and my finger is still a smelling, festering boil. It reeks of death. So he was able to take one for the team and discover that X-rays were in fact dangerous. So there's a lot of neat stuff like that, but this comes into play if you've ever heard people talk about with science fiction that there might be silicone-based life. That's because silicone is in the same column as carbon. Therefore, you'd expect it to behave like carbon. So it might not be quite as strong because it's lower down. It's not going to bond as tightly as carbon does, which is why we use, carbon octanes and so on and so forth for our fuel. Specifically, it has a strong bond and even a stronger double bond. And that energy that's given off basically when you break that bond is what we use for gas. But it also happens to be a strong bond that allows proteins and things like that to be formed. So you could also, in principle, do silicon, and it'd be slightly weaker, but it would still be a different type of life. Germanium, strontium, lead-based life would be a possibility. Remember, Pb is lead, and that's from the word for lead in Latin was plumbum. So that's also where we got the phrase plumber, because they made their pipes out of lead, even though they knew it was dangerous, by the way. So anyways, let's go back to stopping the share. So we've now talked basically about how the periodic table is put together. You still need to read about the alkali metals, the halogens, and stuff like that. The halogens, by the way, on that periodic table were the column right to the left of the noble gases. The alkali metals, of course, was the first table, was the first column. And then, of course, you look at it and learn what the valence is. It'll tell you, for instance, the alkali metals have a valence of +1. The halogens have a valence of -1. So those are terms that you should know, and you probably already know. That's why I'm not taking time to do much work with them. But we've now finished chapter 28. So I'd like to allow you guys to ask me any questions you might have before we go on to chapter 30. Anyone? Anyone?
For that lab, was it only part B that we had to do?
B and C. You didn't have to do part D, as in dog. Talk about the lab last time, right?
Yes. Okay.
Yeah, and I'm cool with you guys sending me those emails to ask questions about it. It's fine. Basically, I will be going through your labs. I'm trying to get some of them done today after I finish this with this practice test stuff. I'll be finishing some of them. Basically, if you got everything right, you're going to get 100. If you made 1 or 2 mistakes, you might have a point or two taken off. But everybody's probably going to have on the order of, if they did all the parts, you're basically going to have somewhere between a 90 and 100 on your lab, but more likely 95 or higher. So don't ever worry about your lab grade bringing you down unless you just skipped the whole chunk or just didn't do it at all. So, but I'll have some of those graded probably tomorrow.
I have a question.
Yes.
So I joined the class late, so I wasn't here when you guys did lab 1 and 2. Should I still do those also, or would those not count against me?
Yes. If you do lab 1, that's the spreadsheet review. That's one you can certainly do on your own. do that and turn it in, and then basically there's no such thing as excused absence. So if you do those, I can give you full credit, and it'll be like nothing ever happened.
Okay.
And the second one is the E-field. Try that on your own. You might even share your information with another student, and maybe they can help you walk you through it. Just turn it in when you can. I think I left the deadlines open on the actual turn-in links. So you should be able to turn in lab 1 in the lab 1 spot and lab 2 in the lab 2 spot. If you ever find there's a problem, just turn it into another one and send me an email so I'll know where it is. But I'll give you full credit. I won't take any points off or anything like that. But feel free to email me for questions.
Okay.
All right, looks like we got almost everybody here today. We've got 23 people. I'll have to take a roll in a second. So we're at the 1 hour mark. I'm going to go ahead and give you guys a 10-minute break. And let's say come back here at 10:40.
Hey, Professor, I had a question
Yes, sir. Go for it.
about the construct the telescope. I wasn't sure about how to do that on that.
You're not doing that part at all. That was part D, if I remember
I'm
correctly.
sorry.
You got that? You don't have to do it?
Okay.
See, these labs getting easier, aren't they?
Right. So for part C, it says multiple lenses on there.
Uh-huh.
And it said like object position and then position of the lens, but it doesn't say on the simulation about the position of the object. So I was confused on that part.
Right. I sent an email to someone about this. So positions aren't relevant at all. If you notice, the equations are 1 over f is equal to 1 over the object distance plus 1 over the image distance. So the image distances and object distances is all that matter. The magnification is even in terms of the object or the image height and the object height, the image distance and the object distance. So that's what you need. The reason we had positions on that lab is because we were using the optical bench. That's why I showed you that meter stick and showed you, we read the measurement off here. You don't need those measurements at all, as long as you got the image distance and the object distance.
Okay.
So remember, the image distance is just the distance between the lens and where the image is, and then the object distance is the distance between the object and the lens as well. What you're going to do is you're going to calculate, forget that second lens, the first lens that the light from the object hits. You're going to use a thin lens equation, the 1 over f equals 1 over d object plus 1 over d image, to solve for the d image. So you might want to write that down. You're going to use that thin lens equation to solve for the image distance on the first lens. Then you're going to use that image distance and that object distance to calculate the magnification. Magnification is negative d image over d object. Then you're going to take that magnification and you're going to multiply it by the object height, and that'll give you the image height. It's going to be huge, like way bigger than the one that you had. Also, the image distance that you're going to find is going to be really huge, meaning it's literally going to be past the other lens. Okay, so it's going to be literally on the right-hand side of the second lens, which is on the right. Now you take that image and pretend like it's the object for the second mirror, or for the second lens, and again use the thin lens equation, 1 over f equals 1 over d object plus 1 over d image. Find out where the new image will be, and that's measured from the second lens to where the image will be. So that's different than the 54.6 or whatever we had from the lab data. You've got to convert it to that type of data. And you can also now take the image height and use that as the object height, use DI and DO to calculate the magnification, and then use magnification times image height, or excuse me, object height to get the image height, and that you can compare to the 3 centimeters that the data gave you. So it's a multi-step process. That's why it's such a wonderful problem in the lab. It gives you a chance to do a really robust college/university level science question that doesn't require calculus and all that good stuff, but still requires some basic arithmetic and algebra. So I'll recap it real quick, and we're probably going to push the time we return from the break back just because I'm helping Isaiah here. So Isaiah, the first step, thin lens on lens 1 to calculate DI. thin lens on lens 1 to calculate DI. Step 2, use DI and DO to calculate the magnification.
So
From
can
thin
you
lens.
repeat that?
Yeah, step 2 is use DI, the image distance, and DO, the object distance, to calculate the magnification from lens 1. Step 3, you ready for step 3?
Yes.
Step 3, use, you're actually using the magnification equation, but just say multiply magnification times the object height to get the new image height.
So magnification times what?
The object height gives you the image height. You end up getting a magnification like negative 2.5 or something like that. So it literally makes it 2.5 times bigger than the actual object was to begin with. So you end up getting around 11 centimeters as the height of the image after the first lens. Now, step 4 is you're now going to use the image from step 1, that image distance. You're going to correct that for how far away it is from the lens 2. So like, let's say it's like 60 centimeters. Well, the other thing is 25 centimeters away. The lens 2 is 25 centimeters away from the first lens. So you have to subtract that 25 centimeters from the 60 to get the distance from the second lens. So your step 4 is really determining the image distance for the second lens, given that the image from the first lens is the object.
Okay.
Okay, if you get answers that are wrong, think that you probably did the sign wrong on one of the image distances or object distances.
Okay.
Now, the next step, 5, is again, use DI and DO to calculate the magnification. And then multiply the magnification times the new object height, and that'll give you the new image height. So step 6 is multiply the magnification times the object height, which was the image height from the previous one, to get the new image height.
All right.
Okay, it's a long process, but like I said, I got really low error, like right at 1%. I think 1.3% was the worst I got. So if you're not getting near there, you've done something horribly wrong. You might want to ask another student for help, or you can just send me another email or whatever.
All right.
Okay, and I'm being pretty, because I'm not being able to grade stuff as quick as I'd like to. I'm also being pretty generous. If y'all are running a little late, you got some other classes kicking your butt. It's okay if you turn in a late lab. Just don't have to turn in 5 of them on the last day of class, because that will kill me. So, if it's a day or two late, it's not gonna be a big deal to me. But don't let any of them go more than a day or two late. Okay.
Professor?
Yes, ma'am.
I know I'm running late on my labs 5 and 6. I've just gotten most of it done, but I'm stuck on like 2 parts for each of them.
Okay.
The lab 5, like the magnetic diffraction or deflection or whatever.
Right.
The equation that we put into Excel, I am confused as to which one. I've rewatched the recording that you have about it, but I'm still a little confused as to what to put in there.
Okay. Again, communicate with another student if necessary, but also at lab today, or maybe even in between the break between lecture and lab today, I'll get you to share your screen and pull up Excel, and I'll pull up my lab report and help you with that. The one thing I'll remind everybody, and I found literally probably 5 out of 6 people that asked for help, the mistake they were making was they took the cosine of 15, but when you say cosine of 15 in Excel, it's not using cosine of 15. It's thinking you're saying cosine of 15 radians, not cosine of 15 degrees. So you've got to multiply that 15 times pi over 180 inside the cosine to use it. So that's one error. If you sort of understood everything else, you might be fine. But otherwise, just be prepared. Have your Excel spreadsheet out and be willing to share your screen with me later on, and I'll walk you through it.
Okay.
Anybody else that has the same problem, please do. And don't worry, like I said, if you're late, it's no big deal. I'll work with you guys.
Okay, thank you.
No problem. All right, so let's make it 10:50 instead for the end of the break. So everybody come back at 10:50. I'm gonna write this here. Hey everyone, I'm back. So we had a few questions about lab and stuff like that. Anybody else have questions on anything? Can't believe I recorded that whole break. What a crackhead.
Professor Younger, on
Yes,
the
sir.
syllabus, it said that the lowest lab grade is dropped. Is that still true?
Yeah.
Okay, thank you.
Yeah, I always do that anyway. So your grade will be good in the lab. Don't worry. If you guys are consistently trying and turning everything in, 99% of my students get 100 for their lab grade. Okay.
Thank you.
So you'll be good. All right. Any other questions? All right. Well, what's next is we're starting into chapter 30, which is on radioactivity. What is radioactivity and all that good stuff. So we're going to talk about, actually, we're going to go 30 up through section 30-4, which is alpha radiation. Next time we'll do beta decay and some other stuff. But this section is actually pretty quick, just because it's fundamental stuff, but it's really simple. Like the fancy math that you're going to do is multiply and divide and take a third root, maybe even subtract. So it's not going to be too bad. So this chapter is called Nuclear Physics and Radioactivity. And we will sort of talk about half-lives. So it was discovered basically in the late 1800s, and later on other things were in the 1900s, but basically in the late 1800s, people were discovering that basically when they left rocks that they had found in the earth in a drawer with photographic film, the photographic film would be exposed, even if the photographic film was wrapped up in light stopping paper. That ultimately turned out to be uranium ore that was irradiating the photographic plate. So that was a kind of interesting process. Madame Curie and her husband Pierre then discovered two radioactive elements, polonium and radium. And again, they didn't really know that these things were necessarily dangerous. And poor Madame Curie, and I think Pierre too later suffered as well. But Madame Curie had some really bad cancer issues with regards to this radioactivity. So I want to express to you what we're talking about in this radioactivity here. We're talking about photons to some extent. That's called gamma radiation. And I mentioned this before, but I was sort of talking in terms of particles. So I want you to understand. I said the first particles, which I really should have said the first radiation, but the first particles / radiation that was discovered was called alpha radiation. And it really was the radiation that was discovered. They didn't necessarily know it was particles. They just knew that, oh, wow, this thing is, causing photographic plates to expose. So they called that alpha. Then another one, they just called it beta, and then another one they called it gamma. And in fact, Rutherford went on to study these things, and he was the one that had seen that the alpha particles turned out to be positive. The alpha radiation turned out to be associated with positive charges. The beta radiation turned out to be related to negative charges, and then the gamma turned out to be neutral items. So ultimately, we discovered that the alpha was the alpha particle that he had already studied when he came up with his sort of solar system model of the atom. The beta turned out to be electrons, and which we also used to sort of feel out the structure of the atoms and how they're made, and how he had to, map out the actual size of the nucleus, even though nucleus is really a quantum thing, so it doesn't actually have a physical size. It has a rough estimate of the physical size. And then, like I said, the gamma radiation turned out to be photons. So we're going to explain all of those things. But before we do so, we need to take on some information that probably most of you already know. So I'm going to turn on my document cam. And then I'm going to pull out my pen and start writing some stuff. But basically, what we discovered ultimately from various sources was that the nucleus was in fact made up of protons and neutrons, and that the mass of the proton was about 1.67. Here's where we're actually going to need a lot of digits, so I'm going to go ahead and use all the digits that our textbook provides. So that's 1.67262. You'll see later why we need all of them. Times 10 to the negative 27th kilograms. That was the mass of the proton. We already knew that it had the same charge as the electron. So it's 1.602 times 10 to the negative 19th, except it's a positive charge as opposed to a negative charge. The English physicist James Chadwick in 1932 had actually discovered the neutron, and its mass, Mn, is 1.67. Notice how close they are, 1.67, but now it goes different, 493 times 10 to the negative 27th kilograms. So that's the mass of the neutron. And you can tell that these weights are much, 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 much bigger than the mass of the proton, of the electron. So if you take, for instance, let's just take to 2 decimal places, 1.67 times 10 to the negative 27th kilograms, which is the mass of the proton slash neutron, divided by 9.1, 9.109, that says 9.12 times 10 to the negative 31st kilograms. And that's the mass of the electron. When we do that, we get roughly a factor of about 2,000. You can actually divide it if you want to. It's not that critical that you have so many sig figs. The main thing is that we see, if I solve this for the mass of the proton and neutron, I get the mass of the proton or neutron is about 2,000 times the mass of the electron. So when we're thinking about atoms, for instance, if you're thinking about the mass of the hydrogen atom, it should be very, very close to that. But in fact, if you add the electron mass in there, we should be around the thousandths of basically around the thousandths decimal place. So 1, 2, tenths, hundredths, thousandths. So right around in here, we might get a slightly different digit if we include the mass of the actual electron. Now, it turns out these particles are the inhabitants of the nucleus. Those particles are also called nucleons, and the individual nuclei are referred to as nucleides. So these are nucleons. And a whole nucleus compared to another whole nucleus, so like an alpha particle and maybe a uranium nucleus, these are called nucleides. Okay. Now, there's a couple numbers that come in handy. We've already talked about the atomic number, and the atomic number really is actually supposed to be the number of protons. And we've already discovered that in the Bohr formula is really the major factor that dictates the energy spectra, or the spectra in general, of elements and compounds. So we see that the number of protons really is the indicator, and that's why we were so fortunate, because each element has an entirely different Z, i.e. atomic number. Therefore, those spectra are a fingerprint for the individual elements present. And it turns out that when you start dealing with molecules, the same thing's true as there. Specifically, each spectra is different for each molecule. So we already know about the Z. The Z is really the number of protons, and it's technically a capital Z. I always put a cross on it, and I think that means a lowercase z, but I'm afraid of it being confused with a with a 2. So I'll put that on there, even though you should all know this is a capital Z. This is actually called the atomic number. And it's equal to the number of protons. There also is another number called A. It's also capital, and it's called the atomic mass number, or just the mass number. So what it turns out to be is really the total number of nucleons. And it's kind of weird, but the reason they're using atomic mass number or mass number is because there's a certain system of units where the proton and neutron are very, very close to a mass of 1. Okay. And therefore, when you start adding protons and neutrons, if you have a 7 protons or 7 total protons and neutrons, maybe you have 4 protons and 4 neutrons and 3 protons, then that atomic mass number is 7, because that's how many particles is there, but it also happens to be fairly close to 7 in a very specific unit of mass. So we can actually take a chemical symbol, for instance, H for hydrogen, He for helium, Li for lithium, Au for gold, or Ag for silver, or Pb for lead. We're going to call that just plain X. And the way we indicate these numbers is X, A, Z, like that. But you can probably tell now that Z is really redundant, because Z corresponds to the number of protons. And we know hydrogen has exactly 1 proton. So just having the symbol H already means Z is 1. Having the symbol He means Z is 2. Having the symbol Li means Z is 3, so on and so forth. So it is redundant. So often we'll just write A as a superscript with X after it. And that actually gives us all the information we really need to know. If you want to know the number of neutrons, obviously Z is the number of protons. A is the total number of neutrons plus protons. So N equals number of neutrons is actually just equal to A minus Z. Okay. So for instance, there is H2. Ooh, wrote that in the wrong place. H2, sorry. H2. I was getting ready to write helium and I changed it, decided to do this. So H2 means that A is equal to 2. See how that looks like my uppercase Z? That's why I put a cross on it. A is equal to 2, and Z is actually equal to 1, just because the symbol H means it's 1 proton. So this means the neutron number is A minus Z, which equals 2 minus 1, which equals 1. So this is what we call deuterium. And your book actually will talk about deuterium a little bit. There's deuterium and there's tritium, and then the individual nucleus is called a deuteron and a triton for the tritium. And actually, it's kind of weird. I was trying to remember exactly how to spell. There it is. I was actually trying to make sure I knew right how to spell deuterium. That's Deuterium. And it's deuterium. Dew is in. There was a movie one time. I can't remember what it was, but Part Dew. Maybe it was an airplane or something. I can't remember. But Part Dew was what it called, and they meant Part 2. So Dew should make you think of the number 2, and it is specifically because it actually has 2 particles in the nucleus. So that's deuterium, and the nucleus itself is called a deuteron. So that's Deuteron. And then there's 3 hydrogen, which means, again, in this case, A is going to be 3, but Z has to be 1 because it's still hydrogen. So N would actually be 3 minus 1 equals 2. So they call this one tritium. Notice that is not corresponding. Deuteron corresponds to 2, which is not the number of neutrons. It's the total number of nucleons. Similarly, tritium corresponds to 2 neutrons, but the nucleon is what gives it the prefix tri. And that particle, that nucleus, is called a triton, which is kind of cool. So I kind of like those words. But anyways, if you've ever heard of heavy water, water is made of H2O. So you can make heavy water out of deuterium. That would be a heavy water, but you can also make it out of tritium, and that'd be another version of heavy water. So this is just some of the basics of nuclear discussion. These individual types of hydrogen. So I've had hydrogen 2, hydrogen 3, but I could also have hydrogen 1. That is A equals 1, Z equals 1, and N equals 1 minus 1 equals 0. That's just plain hydrogen. Okay, so we just call that, no, I wrote that down too low. That's just plain hydrogen. So each of these are called isotopes, which y'all might recognize from Simpsons, The Simpsons. That was the name of the, I can't remember if it was a football team. Yeah, I think it was a football team. The Springfield Isotopes. So anyways, isotopes are really different nuclei of the same element, okay? So they all have the same Z number, but they have different A's. Other examples are, for instance, carbon 11 through carbon 16. So carbon 11, carbon 12, carbon 13, which I think y'all are probably most familiar with, even though you're mostly experiencing carbon 12, carbon 14, 15, and carbon 16. So since C corresponds to Z equals 1, or excuse me, Z equals 6, since C has Z equal to 6, then that means this one has 5 neutrons, this one has 6 neutrons, this one has 7, this one has 8, this one has 9, and this one has 10. So those are the neutron numbers for those particular isotopes of carbon. And basically we define a new unit of mass called the atomic mass unit. Such that the nucleus of the carbon 12, actually I think it's the whole carbon atom, the carbon atom itself has a mass of 12U. And let me double check that, I want to make sure. Yes. So the carbon 12 atom, so if I go 12 carbon equals 12.000000 U, okay? And that's a neutral carbon atom. So that's the new unit that we'll use, the atomic mass unit. And it just so happens, if you think about it, look, carbon 12 has basically 12 electrons, which is crap in terms of weight, right? It's literally 1/2000th of a mass of a single proton or neutron. This sucker has 12 protons and 12 neutrons. So it's literally like 4,000 times the mass of the electron. It's really, really, really high. So anyways, with that, you can realize this is essentially the mass. It's a little bit high, essentially the mass of 6 protons and 6 neutrons. And 6 protons and 6 neutrons weigh about the same. And even once you take into account the fact that the hydrogen atom does have an electron, that actually brings you a little bit closer so that you can realize that the hydrogen atom has a mass of very close to 1U, but the hydrogen atom, if you actually look on a periodic table, it has a mass of 1.00794 as the actual mass. So it's not exactly the same, but it's pretty darn close. And guess what? If you take 1.00, basically 1.0 grams of hydrogen, you get 1 mole of hydrogen. And 1 mole of hydrogen would mean 1 mole of protons, because the electrons are so light. And then 1 mole of protons really would be 6.626 times 10 to the negative, or excuse me, 1.6, messing up on Avogadro's number. Hold on a second. Let me double check before I say a number wrong and make everything screwed up. Whoa, Avogadro's number is not where I expected it to be. Oh, there it is. Yeah, 6.02 times 10 to the 23rd. So it turns out, and this is the whole reason for me to tell you this, is I have a hard time remembering what this converts to. But if I take 1 over Avogadro's number, which obviously I thought I remembered, but I just screwed up there getting it, I get 1 divided by 6.02 times 10 to the 23rd. When I do that math, I actually get something that's close enough for most calculations, not on the nuclear side, but definitely for most calculations. So I'll say 1 divided by 6.022, because I actually know it's 6.022 e to the 23rd. And I get roughly 1.66058, way too many digits than I really want to use here, times 10 to the negative 24th kilograms, or actually it should be 27th if you do kilograms. And lo and behold, the actual conversion for the U is 1 U. I'm gonna write it down here. So 1 U is actually equal to, and this is the exactly right value, 1.6605 times 10 to the negative 27th kilograms. This should have been grams. Okay, so if you do take Avogadro's number, what you're going to get is the number in grams, basically. But if you want it in number, dang, I heard it backwards there. But if you want it in kilograms, it's the same number. Notice 1.6605. I really should have rounded this to 0.6, but lo and behold, the actual figure is 0.5. So it's very close, and it's right on the money up to 3 decimal places. So this is a decent approximation to what U is, but this U is something we're going to use because it's such a small unit. It allows us to deal with masses of nuclei and even atoms as, 1, 2, and 3. So, it's not uncommon to talk about a 12U atom, for instance. Okay, so that's why we're using that unit at all. Now, that's sort of the background stuff that you need to know for nuclear is just atomic mass number, the atomic number, the number of neutrons, and then the units that we're going to use, what isotopes are, what nucleons are, stuff of that sort. Now we can start to get into roughly what Rutherford and other people were able to discover. So when Rutherford started banging at the nucleus with various things, alpha particles obviously was his first thing, but he started using electrons and so on and so forth. He was able to conclude that the radius of the atom, of the nucleus, is on the order of 1.2 times 10 to the negative 15th meters times a to the 1/3 power, where a is the atomic mass number. So the total number of nucleons, basically, right? Now, this is approximate specifically because it's a quantum thing. The nucleus of an atom is a quantum thing. It doesn't have a well-defined radius. But if you want to know roughly what kind of space it takes up, you can use this radius and then calculate volume, assuming it's a circle, is 4/3 pi r cubed. And you get that V is roughly proportional to just plain A. So the volume of the nucleus is basically proportional to A. What that means is when you go from A equals 1 to A equals 2, then you're going to go from a hydrogen to a deuterium, for instance. The volume should roughly double, and so on and so forth. So those are the types of calculation we're going to do. Let's look at an example. Let's say, what is the difference between the smallest atom that we know of, since the smallest atom would be the one with the smallest A. The smallest A happens to be atomic number equal to 1. And the largest naturally occurring one is uranium, which is A equal 92. So let's calculate what the size differences are. So if I look at hydrogen 1, and I look at uranium, in this case, I'm going to take 238, which is the most prevalent occurring one. They're all, every sample of uranium that you have, unless you've done a lot of work to get rid of certain parts, but basically every sample you're ever going to have is going to have some radioactivity. And what you end up doing is you take all the isotopes. I didn't mention that earlier. Let me rephrase that real quick. When I suggested these were the 3 isotopes of hydrogen. Those are the 3 naturally occurring. This one's the most prevalent, like 99.96%. I'm just making that number up, but I wanted to give you an idea for what it is. It's on the order of 99% is this type. And then, about 1% would be this type, and, some itty bitty, even smaller percentage would be what's left over, and that's this type. So if you take the mass of this one and multiply it by, if the number really is 99.96, you multiply it by 0.9996. And you take this one and multiply it by 0.011, say, if that was the percentage, and this one by 0.002 or whatever adds up to be 100, and then divide all those by 100%, that sum by 100%, you'll get the actual mass of 1.00794. So that's the mass that they give you in the periodic table. It really is the weighted averages of all the possible isotopes. So when you see carbon, and you look up there, lo and behold, it does not weigh 12. In fact, on the periodic table, the carbon weighs 12.0107. So that's because it took the each of these isotopes masses and multiplied it by its percent likelihood of finding it here, or its abundance, if you will. Same thing with this one, 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 same thing with this one. Added all those numbers up and divided it by 100%, which is just 1, of course. And then you got the 12.01 number. All right, so back to this. So if I want to consider how big the radii are of these two, I can just say, okay, well, the radius of one hydrogen is equal to 1.2 times 10 to the negative 15th meters times, in this case, it'd be 1 to the 1/3. And I will divide that by the radius of 238 uranium, which in this case is going to be 1.2 times 10 to the negative 15th meters times A, which in this case A is 238 to the 1/3. And I actually should have done the big one over the small one, but it doesn't matter. I'll just flip it over later. So what I'm going to get is, notice the 1.2 times 10 to the negative 15th doesn't come into the calculation at all because they cancel out. So I end up getting 1 divided by 238, and I'm raising that to the 1/3 power. And I get 0.161364, or flipping it over, I could say the radius of 238 uranium over the radius of 1 hydrogen is equal to 6.19715. So what we see is basically the radius of uranium-238 is about 6 times the radius of 1 hydrogen. So the actual nuclei don't vary that much in size from the smallest to the biggest. The factor change is only about a factor of 6. So that's kind of an interesting thing to discover. If you want to talk about something else that's kind of interesting, you can talk about the actual densities of the nucleus compared to regular matter. So for instance, if you consider the density of water, that's about 1,000 kilograms per cubic meter. It literally is basically what we call a metric ton. It's basically 1,000 kilograms, which is, about 2,200 pounds for a whole for a whole cubic meter of water. Whereas the nucleus is going to be a much, much higher density beast. So let's look at the density. Remember, we use the symbol rho for density of the nucleus versus the density of the atom, okay? The atom is not just a nucleus, it's the actual nucleus plus the volume of the individual electron orbits and all that good stuff. So when we go to do this, what we can say, it's the mass of the nucleus divided by the volume of the nucleus. That's what density is. Remember, density equals mass over volume. And this will be the mass of the atom, divided by the volume of the atom. So we can compute that. We can say it's roughly the mass of the nucleus divided by the mass of the atom. And now we have the volume of the atom will actually appear on top. So it'd be 4/3 pi r atom cubed over 4/3, because now the volume of the nucleus will be on the bottom, pi r nucleus cubed. Well, I think you can tell that the mass of the nucleus and the mass of the atom, they really only differ by the mass of the electrons. So that's like 1/2000th of the mass, actually 1/4000th of the mass, because you usually have a proton and a neutron for just about every electron. So this is essentially equal to 1 for this. The 4/3 pi's, they cancel out, and all I get is the radius of the atom divided by the radius of the nucleus. Well, we know the radius of the atom is roughly 10 to the negative 10 meters, and we know the radius of the nucleus is roughly 10 to the negative 15 meters. But both of these things have to be cubed, so that makes it quite different. So I get the nucleus density divided by the atom density is on the order of 10 to the negative 30 over 10 to the negative 45 r. That'll be basically the 45 will eat up all the 30, eat all of the 30 and leave 10 to the 15th. So we'll end up getting 10 to the 15th in the numerator. So the density of an atom is really, really small compared to the density of a nucleus. A nucleus is about 1 with 15 zeros after it, times stronger, or excuse me, times denser than the density of the atom. That is a super, super dense thing. So water, like I said, was 1 times, or excuse me, 1,000, which would be 1 times 10 to the 3 kilograms per cubic meter. You'd expect the nucleus of the atom, or excuse me, of the density of the nucleus to be on the order of 10 to the 18th kilograms per cubic meter. We've done these calculations before. For instance, a neutron star, a white dwarf star, all those things are very, very dense. A white dwarf is actually just very densely packed carbon. But if you go further and get to a neutron star, you're actually talking about a pile of nuclei, specifically a good fraction of neutrons stacked together and attracted to each other. But it's about the size of, a city, and it's as tightly packed as a nucleus. And in fact, a single tablespoon of material of the nucleus, which would be a neutron star or a nucleus, would weigh about as much as Mount Everest. So that gives you a pretty big feel for how dense the nucleus is. Any questions on that? Okay, so the next thing we need to talk about is basically binding energies. I've hinted at this before. For instance, I told you when you take the mass of 2 protons, the mass of 2 neutrons, and you add them up, you get a mass that is actually bigger than the mass of the alpha particle, which is literally just 2 protons and 2 neutrons binded to each other. So the big deal is E equals mc squared is not only true, but it's true all the time. So what I mean by that is if there's any energy stored in, 2 neutrons and 2 protons binding together, that energy had to come from some change in mass, because E must equal mc squared. So lo and behold, when you try to calculate that, you do find out that the mass of the helium nucleus is quite a bit smaller than the mass of hydrogen nucleus. Okay, or excuse me, the sum of the masses. So for instance, we might want to say, compare the mass of the helium-4 atom to the total mass of its constituent particles. So when we're talking about helium-4, remember helium is element number 2, so A is actually equal to 2, or excuse me, Z is actually equal to 2. So helium-4 means we have A equals 4 and Z equals 2, which means N is equal to 2. If we look up the mass of two neutrons, we look up the mass of a neutron, we'd say 2 times the mass of the neutron is equal to 2 times, and now I'm going to use that wonderful atomic mass unit, and the atomic mass unit for the neutron is 1.008665. All these masses, by the way, will be provided to you in table form and stuff like that whenever you take a test. Plus, we have the mass of, for an actual hydrogen atom or helium atom, we have basically not only protons and neutrons, we also have the electrons. So one way you can sneakily deal with this is you can actually look up the mass of in the tables, and the table masses that your book gives you are actually the masses of the atoms. So that includes the actual electrons. So if you look up the mass of the actual hydrogen atom, it's 1.007825. Well, that's just 2 protons bound together. Hydrogen, that's just 1 proton with an electron binding it. We actually need 2 of those. So what I can do is I can say 2 times the mass of H1, and that'll give me the mass of the 2 protons plus the 2 electrons. Cool. Plus the 2 electrons that helium has. So I actually get real values. That value is 2 times, now the mass of the actual hydrogen atom is 1.007825. Again, these units are U, atomic mass unit. When I add those up, I end up getting basically, well, first off, you got to multiply them. When you multiply them, you get 2.0173. And when you multiply this one by 2, you get 2.02 or 0.0, oh yeah, 14, sorry, because I multiplied it by 2, not 3. 2.01 and then 4, but I also multiplied by the 8 here, so that made 16, so that gives me a 5 instead of a 1, and then a 6, but I also multiplied by 2, so that gave me a 12, so that made it a 7, so on and so forth. So you end up getting 5650 U. When I add those up, I get a total mass of 4.0329980 U. So that's the mass of the constituent particles. In other words, all the parts together, but not collected as a helium nucleus. Now, the mass of the actual helium atom, which is really what we did because we took the nucleus plus, including this, that counted as our 2 electrons. So I can actually use that now and look up the mass of the helium nucleus. And the mass of the helium nucleus turns out to be 4.002603. Equals 4.002603 U. So you can see clearly the mass of the constituents is 4.03, whereas the mass of the, whoa, did I get that far off? Yeah, that's right. Whereas the mass of the individual helium atom is 4.002. So you can see it's quite a bit smaller. In fact, that difference in mass, you take 4.032980 U and you subtract from it 4.002603 U. 10 minus 3 is 7. 7 minus 0 is 7. 9 minus 6 is 3. 2 minus 2 is 0. 3 minus 0 is 3. 0, that 0. So that individual mass is 0.030377. That's the individual difference in mass. If I then converted that to kilograms and multiplied it by c squared, that would give me the actual energy, what we call the binding energy of the helium nucleus. So let's do that. So the binding energy is equal to delta M times c squared. And this is delta M, we just computed that, times c squared. Well, delta M is 0.030377 U. And we worked out earlier that basically the U mass is 1 over the atomic mass unit, or excuse me, 1 over Avogadro's number. So that's 1.6605 times 10 to the negative 27th kilograms per U times C squared. And C, of course, is 3 times 10 to the 8th meters per second. We don't really need to go more than 2 decimal places on that. So let's multiply that out and see what happens. Now this is going to come out in joules, which is not a convenient unit, so I'm going to convert it to electron volts in a second, but 0.030377, multiply that by 1.6605 times 10 to the negative 27th, and that's kilograms per U, times 3 exponent 8 squared, and I get 4.54. Let's do 540 times 10 to the negative 12th joules, but 4.540 times 10 to the negative 12th joules times, in this case, I'm going to divide it by 1.602 times 10 to the negative 19th joules per 1 electron volt. And I think you can see we're going to get something really big. Divided by 1.602 e to the negative 19. That gives me 2.834 times 10 to the 7th electron volts, or, check this out, 28.3 mega electron volts. So that's a mess load of energy at that level. That is the binding energy of the helium nucleus. And in fact, experimentally, we've determined it to be 98.30 MeV. And we can even use a different mass unit that actually makes life a lot easier. So often, instead of using U or kilograms, we'll use a unit like electron volts per C squared, or mega electron volts per C squared, or stuff like that. And if you want to try that, the values that you're going to use from time to time are just that. For instance, the electron has a mass of 0.511, or excuse me, 511 kilo electron volts, or 0.511 mega electron volts. So the mass of the electron, which is 9.109 times 10 to the negative 31st kilograms, is also equal to 0.0005485 U, but that's also equal to 0.51100 MeV per C squared. So if you move the decimal 3 places here, that would be multiplying by 1,000. If I divided this by 1,000, I'd get kilo. So you see the mass of the electron is about 511 kilo electron volts. Similarly, the mass of the proton, we already knew that in kilograms was 1.67262. Kilograms, and that of course equaled 1.007276 U, and that actually turns out to be 938.27 MeV per C squared. So what that means is this just gives you a really quick way to calculate the energy. If it's a proton, you know it's 938.27 MeV. That's it. You don't have to do the thing of multiplying by C squared, because you're just multiplying by C squared and it automatically cancels out. The mass of the neutron, on the other hand, is 1.67493 times 10 to the negative 27th kilograms. Again, left off the grams up there. which is again slightly heavier than the proton, but it's 1.008665. Make sure I got the right one. 67493. Yes, 8665. And that's 939.57 MeV per C squared. So notice these are very close to 1,000, which after a MeV becomes a GeV. So we're very close to a single giga electron volt or giga electron volt, if you want to listen to Back to the Future, per C squared is what the masses of those particles are. So we've now learned a way to calculate binding energies. You just take the sum of the parts, but remember all the masses that were given. Your book gives you a table of these masses, and in that table, it's actually giving you the masses of the individual atoms. It's not giving you the masses of the nuclei. So you've got to be wise about that. You just got to remember that, hey, if you take hydrogen and use that for each of the protons, then you're automatically counting each of the electrons for a neutral atom because the number of protons is supposed to equal to the number of neutrons. So just always use hydrogen. For instance, if you're trying to figure out the mass of uranium-238, so uranium-238, uranium actually has a Z number of 92. So if you're trying to figure this out, and you want to know what its parts are, what you want to do is take and say, well, the mass of the hydrogen, which is also the same thing as this, is actually the 92 protons. So I'd say 92 times this, and then that would account for all the protons and the electrons. So that's kind of nice. But then I just do 238 minus 92 to get the number of neutrons. So 238 minus 92, 8 minus 2 is 6, 13 minus 9 is 4, and that's 146. So I now add 146 times the mass of the proton, or excuse me, mass of the neutron. Add those up, and that's actually the mass of it, of its constituent parts. So just by using this hydrogen, it automatically takes care of the stupid electrons. So let's do this one. Let's see what we actually get for a binding energy. So in this case, you say 92 times, we take the mass of the electron, or excuse me, the mass of hydrogen, which is another one we really should use. So I should put it right over here. Mass of 1H1 should equal 1.007825. 1.007825. That's the mass of the neutral hydrogen. So I'm going to take that and multiply it by 92. Since it is the mass of a neutral hydrogen, it is the mass of basically 1 proton and 1 electron. So in this case, I get 92.7199U. And now I take 146 and multiply it by the mass of the neutron, which is 1.008665. And I get 147.265. I suspect my calculator is rounding some stuff down since it's giving me only 3 and 4 decimal places. That might be a problem. We'll see in a second, in which case I'd have to change the settings of my calculator. So I add those two, say plus 92.7199. Whoa. And I get 239.985 U. That's the mass of the constituent parts. If I go and look up the mass of uranium-238, which again is in a table in the back of our book, and I'm going to try to search for that real quick because for some reason I switched to flying by the seat of my pants instead of actually using stuff that I already calculated for you guys. I have to look it up. Okay, so it's not there. It's not Appendix E. Ah, here it is. So uranium-2, I'm looking at Appendix B as in boy now. And uranium, which is atomic number 92, the 238 has 238.050788. Its mass is 238.0507. 050788. So you can see the parts in this case actually weigh more than the nucleus itself. So this one does have a positive binding energy. And what we normally do is we think of that and say, well, whenever the mass of the nucleus itself is less than the mass of the parts, then it is actually a stable nucleus. So uranium-238 is fairly stable. Obviously, it's got a bunch of other things mixed in with any sample of uranium, so it's got all those other isotopes in there too, and they might not be so stable, but that's how you go about calculating the binding energy. So if you want to figure out about radioactivity, what you have to realize is what is going on with radioactivity. So in the case of radioactivity, there's actually several types, but 3 or 4 of them is what we're going to talk about. It's about basically the alpha decay, the beta decay. There's also a beta decay that's a little different than the original beta decay. And then there's actually gamma, and there's an electron capture, which is also kind of weird, but we're just going to talk about the alpha decay today. So what's going on with radioactivity is basically when you find that a nucleus is less stable in its current state than it would be if it was broken up into, in the case of an alpha particle plus another nucleus, such that the atomic mass number the atomic mass number is conserved and such that charge is conserved. Then what you find is that is a radioactive decay that is likely to happen. So when we say something is radioactive, we call the isotope that actually decays a radioisotope or a radionuclide. Notice I'm pronouncing nuclide as if it's like a bunch of different syllables as opposed to just nuclides, but that is actually the way we pronounce it. So radionuclide, which I'll write real quick so y'all know what I'm talking about. Radionuclide is actually pronounced radionuclide. So cleide, it's almost like you got 2 I's in there. So that's the way it's actually pronounced. So that's one type of radiation. And really the type of radiation that indicates is, let's say you have an atomic nucleus with a chemical symbol N, okay? So there's your parent nucleus. It also has an atomic number A and, atomic mass number A and an atomic number Z. Well, by alpha decay, that means it's going to lose an actual alpha particle. An alpha particle is 2 neutrons and 2 protons. So really Z is going to decrease because Z is the number of protons. It's going to decrease by 2. So I'll write this as Z minus 2. And since I also lost 2 neutrons, the total loss to my atomic mass number, which is protons plus neutrons, is 4. So this will be A minus 4. And we would call this the daughter nucleus. And it would be added to for helium-2. So notice this number and this number add up to give you just plain Z, which is the same as this number. And this number and this number, the atomic mass numbers, they add up to give you A. So A and Z are both confirmed. Z really is a confirmation of charge, is one way of thinking of it. But that's what happens in an alpha decay. So for instance, if I gave you that radium alpha decayed, radium-226, which is Madame Curie's element, right? Radium-226, if you look up in the periodic table, you realize that it has 88 protons. Then you automatically know, and they don't really use equals, even though I run equals, they actually use an arrow like you do in chemistry, in chemical reactions, only in this case, it's not a chemical reaction. They, Rutherford and various people literally tried with various nuclei and atoms, tried putting them in acid, boiling them, all the typical things that chemists do to try to break one element into another, and none of them would change the actual isotope at all, much less the whole nucleus. So we know it's definitely a different process. But in this case, we're going to lose an alpha particle. So that means we're going to lose 4 nucleons. So instead of 226, it's now going to become 222. And we're also going to lose 2 protons. So instead of 82, it's going to be, or 86, it's going to be, excuse me, instead of 88, it's going to be 86. So if we look up and find out what element 86 is, we'd see that element 86 is in fact radon, which is also a bad thing. You'll probably heard about that as well. So we already know what element it's going to be, but it also has to add to it a helium nucleus, because 86 plus 2 gives me 88. That matches, so check. And 4 plus 222, that gives me 226, so that checks. So I know that that reaction is real. If I really wanted to calculate what happens here, what I could do is I could take the mass of this and then compare it to the mass of this and the mass of this, and the mass difference between these two and that one added together, these two added together and that one, that would give me the actual energy that's put into the reaction. That energy is basically energy that goes into kinetic energy of this guy and this guy. But momentum still has to be conserved and energy has to be conserved and all that good stuff. So you can actually work out all of it. So let me do one example like that and then we'll call it. So first off, let's look at uranium decay. So uranium, in this case, we're going to deal with uranium-232. So uranium-232. And of course, uranium means 92 for this guy. And they want us to calculate the disintegration energy when uranium-232, by the way, its mass is 232 point. Notice how they're actually giving it to you. I'm actually giving it to you in real time. That's exactly the way a problem would be worked in your homework or on a test. And it decays into, obviously, this is going to go down by 4, so that's going to be 228. And this is going to go down by 2, so that's going to be 90. And if you look up 90, you'll find that's thorium. So it goes to 228 thorium 90. And that has a mass of 228.0288741 U. Okay. What we want to find is how much energy, decay energy is released. Okay. If you want to do that, then what we need to do is figure out how this mass compares to this mass plus the mass of the alpha particle. So the uranium-238, we can just sort of think of that as, well, we know its mass already, so I don't have to put that together, but we add that to the mass of the actual helium nucleus. So we got 228. This is output. I'll write it as output. It's also the products is another way of saying it versus the input. So 228.02874 U. And I'm going to add to that the mass of the alpha particle. And the mass of the alpha particle, you can just look up. Again, this takes into account, since I'm using this is the mass of the whole atom. That takes care of all the electrons, except for the electrons associated with the alpha particle. So we're going to end up adding to that the mass of the alpha particle, which is 4.02 excuse me, to 603 U. When we add those two together, we get 232.03134, 1344, excuse me, U. So that's the output mass. The input mass, of course, is just the 232.083. So we got to really find out what the difference in mass was. So we're going to do 232.03 7156 U minus 232.03134 U. 6 minus 4 gives me 2. 5 minus 4 gives me 1. 11 minus 3 gives me 8. But this one's now 6. 6 minus 1 gives me 5. And the 3 is minus the 3 is 0. And 0. So I get 0.005812 U is the difference in mass. 1 U, by the way, this is a very helpful piece of information. 1 U is 931.5 MeV. So 0.005812 U times 931.5 MeV per U gives me 5.4 MeV. So that energy right there is what goes into the kinetic energy of the daughter nucleus and the kinetic energy of the alpha particle. Well, initially, if we just assume we're in the frame where the uranium was sitting still, then the total momentum should be actually equal to 0. So after this occurs, the total momentum should still be 0, which means that 0 is equal to the mass of the uranium times the velocity of the uranium plus the mass of the alpha particle times the velocity of the alpha particle. But in this case, this is 0 and this is 0. All these were initial conditions. And then after the fact, you're going to have the mass of the thorium. Oh, the alpha particle wasn't there anyways. I shouldn't even put that in there. Plus the mass of the alpha particle. Okay, times velocity in both cases. This is thorium and this is alpha. So we know that the mass of the thorium times the velocity of the thorium is equal to the negative of the mass of the alpha times the velocity of the alpha. And we know that the total energy should add up to give you 5.4. So if you assume these are non-relativistic particles, which certainly they probably are because it's a huge nucleus and an alpha particle, then you can just say the energy is just going to be 1/2 mv squared. So we can say the kinetic energy of the thorium should be 1/2 the mass of the thorium times the velocity of the thorium squared. And the kinetic energy of the alpha particle should be 1/2 the mass of the alpha particle times the velocity of the alpha particle squared. You can add all those two up, but basically what you end up getting is you get that this energy plus this energy has to equal 5.4 MeV. And using that, you can solve, say, for one of the velocities in terms of the other, plug it in here. And if you actually do that algebra a little bit, you end up getting basically that the kinetic energy of the alpha particle is about 57/58 of the total energy. That's what this quantity right here is called. That's called the Q value. If the Q is negative, it's not going to happen. Whatever reaction that you calculate, if the Q comes up to be negative, that means that reaction is not going to happen on its own. You got to do something to make that happen. This case, it definitely came up positive. So when I multiply 57.8 times, or 57/58 times Q, I end up getting 5.3 MeV. In other words, 57 times 5.4 divided by 58 gives me 5.3 MeV, and that's the actual kinetic energy of the alpha particle. The other 0.1 MeV will be the energy of the thorium. Now notice thorium is really heavy, so you don't have to have a very high velocity at all to get that kind of energy. So it'll be going very, very slow, whereas alpha particle might actually be going pretty good speed. If you wanted to calculate what that is, you just use your kinetic energy and solve that for V. Okay. So that's really all the types of calculations you got to be able to do for these radioactivities, at least section 30 through 31 through 34, 30-4. So in terms of everyday life, does this stuff come into play? Well, we've actually found plenty of applications for it. The alpha particle, for instance, is this really, it's a deadly thing in the sense that it carries a lot of energy and could disrupt, all sorts of DNA and stuff like that. And when you disrupt DNA, that's called a mutation. The vast majority of which turn out to be having no effect whatsoever. But every now and then a mutation can really be bad, and that's called a cancer. So that would be bad. The good news is literally a sheet of paper will stop an alpha particle. So you don't usually worry about alpha particles unless you're inhaling them and stuff like that. You still want to stay away from an alpha emitter. For instance, plutonium is an alpha emitter, as is uranium. Anything that you see that has an alpha decay, that's an alpha emitter. Those things are not good for you, so you still want to stay away from them. But the good news is you can stop them very easily. The beta decay, they're a bit more of a problem because they're going to release electrons or even positrons, and those things can penetrate quite a few centimeters of lead, so they're a little more dangerous. Then there's gamma radiation, and the gamma radiation is photons, and they can actually go through several centimeters of lead. So they're even more energetic and potentially more dangerous. But we use, we use particle radiation. So we use protons and neutron. You probably heard Hampton University talking about proton therapy. That is a very good mechanism for treating cancer. We could use electrons, but it turns out that when you shoot electrons at a tumor, it loses its energy sort of in a wide distribution of an area, whereas a proton, when you shoot it into a human body, it has a certain location where most of the energy goes, and then all the rest of the energy dies off really, really quickly. So if you adjust the energy of the proton properly, the proton will just distribute energy, i.e. cause damage to the tissues between the skin and the actual tumor, and then the vast majority of the energy will go only in the tumor and then nothing beyond it. And remember, from the outside of the body to the tumor, that's usually superficial stuff like skin and junk like that, which can handle a little bit more. And they also lessen that effect by rotating the body about the center of that tumor, so that, one day it's coming from one angle, the next day it's coming from another angle. So using protons can actually make collateral damage to organs and tissues a lot less severe. Another actual, and actually all these radiations were used. In fact, I had a friend, an older lady, about 20 years ago. She had breast cancer, and back then, she was in her 70s then. But back in her day, when they started treating people with it, she literally just laid next to a accelerator in a physics department, and she had horrible burns all over her chest that lasted several weeks, but she managed to survive. So it was still a better outcome than had she not done it, but it was really, really painful. That was just basically photon radiation, what we call gamma radiation. So that happens, that can do it as well, but it's a little, generally not quite as wonderful as proton therapy. Finally, a much more mundane thing is a smoke detector. So basically, you put americium, that's a typical radioactive element that they use in smoke detectors. If you put americium in a little evacuated tube, the americium slowly decays. And as it decays, it gives off these little alpha particles. And the alpha particles, which are charged, will cross over to another metal because you got a battery in it that makes an electric potential, sort of like the photoelectric effect, only you don't need the heat or whatever to release it. So the little particle will actually register as a current because it gets a certain number of positive particles going to the negative terminal of the battery every so often. And basically the smoke detector monitors that current. Eventually that current will have something that disrupts it. Remember, I told you alpha particles are really easy to stop. A piece of paper will do it. Well, it turns out smoke particles going into the smoke detector will actually stop the alpha particles as well. So if a little particle of smoke gets in the smoke detector detects a decrease in current and immediately sets off an alarm. So there's a lot of good things that came from these discoveries, but like I said, there's a lot of bad things. There used to be, you used to go to a shoe store and there'd be a floor shine machine, and the floor shine machine was basically an X-ray device that was under your feet and shot literally directly at your gonads through your feet. So you could look at an X-ray of your feet. At the same time, you could look at the X-ray and it had the various sizes of shoes. So you could ideally, you know, match your shoe size to exactly the bones of your feet. Again, people didn't necessarily know that X-rays were all that dangerous, but guess what? You were shooting X-rays right in your gonads. That's the very worst place for your X-rays to hit. So we've had a wild time trying to learn exactly what could happen with X-rays, radiation in general, and stuff of that sort. But in the end, we've actually made a lot of positive and negative discoveries about it. Things that have, you know, in some cases shortened world wars. In other cases, it's powered places in a very green way. So it can, you know, solve the carbon problem that we're having right now. You can do all sorts of good stuff with it, but also you can have a nuclear meltdown and, you know, hundreds of thousands of people can get sick. So there's always pluses and minuses. Does anybody have any questions on that material? There's a lot of stuff, I know. If you read the book, I think it's pretty straightforward for you, though. You just got to know how to do those calculations to find the neutron number, calculations to find binding energy, calculations to find the actual Q, which is the energy given off by a certain decay. And if that Q ever turns out negative, that means it's not going to happen. You have to actually add energy to make it happen. And if the Q turns out positive, that energy is going to be distributed as kinetic energy amongst the two daughter particles, which would be the daughter nucleus and the alpha particle for the alpha decay. So I think that's pretty straightforward. We learned how to assemble the electron configuration for a given atom, assuming the ground state. So that's all fair game. If no one has any questions, what I'm going to do is I'm going to give you I think I'll give you a 8-minute break. Let's be back at 2. Now I'll go ahead and give you, since it's 12:06. Let's be back at 12:10, or excuse me, 12:15. And we'll be on the other Zoom channel at that time. And we'll start up your lab. The lab has been posted, so if you want to go ahead and read over it, you can. There's even a video there. You can even watch that where we describe the types of experiment we're doing, so you can watch that as well. I will see you back here at 12:15, everyone.
I did have a quick question.
Yes, go for it.
It's actually about the test on Friday. So I know before you were saying that we couldn't have our phones out or anything, and then you're mentioning about using it as a calculator.
Oh, so, yeah. Go ahead.
So I was wondering, are we going to be able to use our phones as a calculator? Like, I have one calculator, but honestly, it completely throws me off. My calculator on my phone is way better.
Yeah, I can't let you use your phone for your calculator. That's just, if it was a face-to-face thing, I could do it because I could verify that you put it in airplane mode and all that good stuff, but I just can't do that. You definitely get you a calculator that you feel comfortable with and use it from now till the test time so you get a little more comfortable. And since you already have one, try that one. What problems do you have with it? Anything specific I could help you with on the calculator?
So it's just like it's super basic, what a TI, I forget what this one's actually called.
Not a graphing calculator, it's a small screen.
So it's like not a graphing calculator, it's just literally a scientific calculator.
Okay.
And like on my phone, like the reason why I like it better is because I can go in and I can put things in parentheses and go back and forth and gotcha. Use what I had previously put in there, but with this one I can't.
Yeah, there is actually a way with even with the one you're using. There's a way you can do parentheses and all that stuff. If you want to stay after lab today and pull out your calculator and share your camera with me, I can help you a little bit with that. But yeah, I can't let you use your phone. You might want to try borrowing someone else's calculator, but if you do it, you better borrow it today so you can start on it today. because you probably need, experience with, 10 or 15 problems before you're comfortable enough to use it on a test.
Okay.
Okay, sorry about that.
All good.
Anybody else? All right, well, I'm going to stop the recording and stop this meeting, and I'll see y'all back at 12. Let's make it 12:17 now, I guess.